So I want you to imagine just peeling a piece of everyday plastic stretch wrap off a pallet. You know, like a towering pallet of cardboard boxes.
Right, we've all done it.
Yeah,
Yeah.
exactly. And you hear that familiar little static crackle, right? Maybe you even feel the hair on your arms stand up a bit.
Sure, usually it's just a minor annoyance.
Right. But if you perform that exact same everyday action inside a facility that manufactures organic coatings, so we're talking, automotive paints, marine resins, industrial solvents, that tiny invisible spark of static electricity has the potential to literally detonate the air around you.
It really does. It's terrifying.
I mean, we're talking about leveling the entire building and shattering windows blocks away.
Yeah, it's a very sobering reality because you
Uh-huh.
are dealing with an environment where the atmosphere itself can become this hair trigger explosive. I mean, the human experience of architecture, it usually revolves around like comfort, right? Light,
Yeah.
flow, things like that. But in this industry, you are essentially engineering a highly specialized, heavily regulated cage for, well, an invisible, volatile beast.
A beast, I like that. And keeping that beast in its cage is exactly what we are focusing on today. Welcome to today's deep dive. We are taking a really comprehensive journey through NFPA 35, the 2016 edition.
Which is the standard for the manufacture of organic coatings.
Exactly. But we aren't just here to read rules at you. Our mission for this deep dive is to extract the essential life-saving fire and explosion prevention strategies, and we're tailoring them explicitly for you, the professionals who bear the ultimate responsibility.
Right, the people actually doing the work.
Yeah, so if you are the layout engineer trying to fit massive process vessels into a tight site plan while, designing the fire protection.
Or if you're the mechanical contractor actually putting the pipes and pumps together.
Right. Or even if you are the facility owner whose livelihood depends on maintaining this operation safely day in and day out, this is your shortcut because we are looking at materials where, honestly, a single design flaw can lead to an absolute catastrophe.
Yeah. And what becomes immediately apparent when you really study this standard is that it isn't just some arbitrary list of bureaucratic red tape.
Oh, definitely not.
It's an incredibly intricate, holistic system of physics, chemistry, thermodynamics, and, risk management.
It's all connected.
Exactly. Every single paragraph in this document is a direct, engineered countermeasure to a specific law of nature.
Like how liquids turn into heavy vapors.
Right, or how thermal energy transfers through structural steel, or like you mentioned, how the simple act of a liquid falling through a pipe generates static electricity out of literally nowhere. It is a masterclass in anticipating the absolute worst-case scenario.
So before anyone pours a single yard of concrete or buys a piece of real estate, we really have to understand the fundamental nature of the threat here.
The chemistry.
Right, the chemistry. The standard draws a very sharp, very deliberate distinction between two terms that a lot of lay people just use interchangeably. A flammable liquid and a combustible liquid.
Yes.
So why is that specific distinction the absolute bedrock of facility layout?
Well, it all comes down to a chemical metric called the closed cup flash point.
Okay, what is that exactly?
So this is the temperature at which a liquid gives off enough vapor to form an ignitable mixture with the air directly above its surface.
Just hovering right there.
Right. So if you have a flammable liquid, which the standard categorizes as Class I,
Yeah.
it has a closed cup flash point below 100 degrees Fahrenheit, which is about 37.8 degrees Celsius.
Wait, below 100 degrees Fahrenheit?
Yes.
But I mean, 100 degrees is roughly just ambient summertime temperature in a lot of places.
Exactly. And that is critical. It means these liquids, like standard gasoline or, many of the solvents used in organic coatings, they are constantly off-gassing at normal room temperature.
So they don't even need any help from a heater or anything.
No, not at all. They're already producing explosive vapors just sitting there in a bucket. They're always ready to ignite.
Wow.
Yeah. And the standard also adds a second metric for these Class I liquids, which is Reid vapor pressure.
Reid vapor pressure.
Right. It states this absolute pressure cannot exceed 40 psi at 100 degrees Fahrenheit.
Okay, break that down for us.
Sure. Reid vapor pressure is basically a measurement of how aggressively a liquid wants to become a gas.
Like how badly it wants to escape.
Exactly. A high vapor pressure means the molecules are highly energetic, right? They're pushing really hard against the atmosphere to escape the liquid phase.
Okay, got it.
So a flammable liquid evaporates easily and flashes at room temperature. A combustible liquid, however, which falls into Class 2 or Class 3, has a flash point at or above 100 degrees Fahrenheit.
Ah, okay. So at a normal room temperature of, say, 70 degrees, it isn't really producing enough vapor to ignite on its own.
Right. You actively have to introduce thermal energy heat to make it dangerous.
But, the standard also brings up another metric called the fire point. And I've always found this distinction really fascinating.
It is, yeah.
If the flash point already tells us when a chemical becomes explosive, why do engineers and emergency responders even care about the fire point?
Well, because the flash point is often just that. It's a momentary flash.
Oh, like a quick burst.
Exactly. If a liquid reaches its flash point and you introduce a spark, the vapor layer sitting on top of the liquid will ignite, flash brightly, and then potentially just go out.
Really? It just stops?
Yeah, because the liquid itself isn't vaporizing rapidly enough to sustain the combustion yet. The fire point, which is typically a few degrees higher than the flash point, is the lowest temperature at which a liquid will ignite and achieve continuous, sustained burning.
Okay, I've always thought of it like lighting a traditional gas stove.
Oh, that's a good way to look at it.
Like when you turn the knob, you get that initial poof of gas igniting. That's the flash point, right?
Right.
But the fire point is the steady blue ring of flame that actually stays lit so you can boil your water.
That is an excellent analogy, actually. For the layout engineers and fire protection designers, the flash point dictates the hazard classification of the room.
So whether you need explosion-proof electrical gear or specialized ventilation.
Precisely. But the fire point dictates the sustained intensity of the emergency you're going to be fighting if things go wrong.
Actual fire.
Right. And there is a massive caveat here for process engineers. The volatility rules completely shift the moment you add heat.
What do you mean?
Well, if your manufacturing process requires heating a relatively safe Class 2 or Class 3 combustible liquid up to its flash point, the surrounding area instantly becomes a classified hazard zone.
Oh, wow. So the chemical didn't even change?
Nope. But by adding heat, you've transformed it into a Class I hazard functionally.
Which completely alters how you have to build the facility around it.
Entirely.
And, I mean, that physical reality dictates where you can even place the building in the first place. When you look at the facility layout rules, the standard is enforcing radical isolation.
Radical is the right word.
Right. Because, first off, organic coating manufacturing operations cannot be located in the same building with other occupancies. You can't just put a resin cooking operation on the ground floor of a mixed-use industrial park with, like, a paper goods warehouse or a commercial bakery next door.
Yeah, no, the risk of collateral damage is simply too great. The standard allows for incidental operations, like maybe a small administrative office directly connected to the manufacturing process. But true independent occupancies are completely banned.
Makes sense.
Furthermore, the building must be accessible from at least two sides for firefighting and emergency operations. You cannot wedge these facilities into tight urban alleyways.
But what really caught my eye were the setback distances for the process vessels themselves.
Oh yeah, the tank farm spacing.
Yeah. If I'm an owner or a layout engineer looking at these massive tanks holding, tens of thousands of gallons of solvents, I can't just put them right up against the property fence to save space.
Not even close. The standard provides a very specific table 4.2.3.1 that dictates the separation of process vessels from property lines, public ways, and what they call important buildings on the same property.
What counts as an important building?
Basically, any structure that isn't expendable, like an occupied control center or an administrative wing where evacuation takes time.
Got it.
So for a smaller vessel, say holding up to 275 gallons, you need a minimum of 5 feet from the property line.
That's not too bad.
Right, but for a massive 50,000-gallon tank, the baseline setback is 30 feet from the property line and 10 feet from the nearest public way.
Okay, but that 30-foot setback is just the best-case scenario, isn't it?
It is.
Because the standard introduces multipliers based on the internal pressure of the vessel and the chemical stability of the liquid.
Yes, and this is where the physics of explosions dictate the real estate. Those baseline numbers are for stable liquids in vessels, where the emergency relief venting is set to 2.5 psi or less.
Wait, why 2.5 psi specifically?
Because if a vessel is exposed to fire, the liquid inside boils and pressure builds. If the relief vent pops open at a low pressure under 2.5, it releases the vapor relatively gently.
Okay.
But if your relief venting is set higher than 2.5 psi, the internal pressure is allowed to build to a much higher energy state before it finally releases.
Like shaking a soda can before you open it.
Exactly. And when it finally vents, the release is incredibly violent, pushing that explosive vapor cloud much further across the property.
Wow.
So because of that physical thrust, the standard mandates you multiply the setback distances by 1.5.
So that 30-foot setback immediately becomes 45 feet just because of a vent setting on a valve.
Yep. And the math becomes exponentially harsher if you're processing unstable liquids.
Oh boy, unstable liquids.
Right. These are reactive chemicals that will vigorously polymerize, decompose, or become self-reactive under mechanical shock or temperature changes.
So they're just looking for an excuse to react.
Exactly. If you have an unstable liquid in a tank with venting under 2.5 psi, you multiply the base distance by 2.5.
Okay.
But if the venting is over 2.5 psi on an unstable liquid, you multiply the distance by 4.
That is staggering.
It really is.
So that original 30-foot setback we talked about for a large vessel, if it contains an unstable liquid and has high-pressure venting, you multiply by 4. You now have a 120-foot setback requirement from the property line for a single tank.
Yes.
I can only imagine the sheer panic of a contractor or an owner trying to retrofit modern high-capacity vessels into an existing landlocked urban footprint. I mean, industrial land is incredibly expensive.
It creates massive headaches for facility planners, absolutely.
What do they even do?
Well, if you physically cannot acquire enough land to meet that 120-foot setback, the standard does offer an engineering compromise, but it is a formidable one.
Okay, what is it?
You can waive the distances if the vessels are housed entirely within a building and the exterior wall facing the property line is a blank wall.
A blank wall, meaning?
Meaning absolutely no doors, no windows, no unprotected openings whatsoever, with a minimum 2-hour fire resistance rating.
Wow.
Essentially, you have to build an impenetrable rated fortress wall. And if those are unstable liquids we're talking about, that wall also has to be heavily reinforced to resist structural damage from an internal explosion.
That sounds almost as expensive as just buying more land.
Sometimes it is.
You know, I noticed another really fascinating clause that dictates layout based on emergency response. The code mentions something called protection for exposures.
Yes.
And if you don't have this protection, your setback distances for unstable liquids automatically double. What exactly are they asking the owner to prove here?
So protection for exposures is essentially the NFPA's way of asking, is the cavalry coming? It means you have a public fire department or a highly dedicated private fire brigade capable of arriving quickly and laying down heavy cooling water streams to protect the adjacent neighboring properties from the radiant heat of your burning facility.
Okay.
If your plant is out in a remote rural county with a volunteer department that takes 30 minutes to arrive, or if the local water infrastructure just can't support heavy flow rates, you do not have protection for exposures.
So the standard steps in.
Right.
Yeah.
The standard compensates for this lack of human intervention by forcing you to buy more land. It uses physical distance as the ultimate fail-safe buffer.
It's brilliant because it mathematically links local municipal infrastructure directly to the facility's real estate footprint.
Precisely.
And for the civil engineers listening out there, there is a strict mandate on topographical drainage too, right?
Yes, very strict.
You cannot let a burning liquid spill flow from your process area into an adjacent facility. You have to grade the land and design interceptor trenches to essentially route a river of burning solvent away safely.
Which logically brings us to the structure of the building itself.
Yeah.
We know the behavior of the chemicals now, and we know exactly where on the property the building has to sit.
Mhm.
So how do we engineer a structure capable of actually containing these hazards?
Right. Let's look at the construction of the building itself. The baseline is that the structure must be fire-resistive or non-combustible. But there is a massive architectural prohibition here that we need to talk about.
Of a basement bank.
Exactly. You are legally forbidden from designing or digging a basement. The first floor of the building must be at or above grade. I really want to dig into the why here, because it ties directly back to what you mentioned earlier about vapor behavior.
It is entirely about vapor density.
Okay.
When a highly volatile solvent evaporates, the resulting vapor does not rise into the atmosphere like steam from a kettle or, helium.
Right.
Solvent vapors are significantly heavier than air. They behave almost identically to a fluid.
Like water.
Like water. If a pipe leaks on the first floor, those heavy vapors will cascade down stairwells, they'll flow down elevator shafts, and they'll pool in low-lying areas.
Wow.
So if a facility have a basement, that subterranean space acts as a massive, invisible collection basin.
A completely silent trap.
Exactly. A relatively minor spill-up on the operating floor could result in a basement that is completely saturated with an explosive vapor-air mixture.
Without anyone even knowing.
Exactly, because basements generally lack natural cross-ventilation. So the vapor just sits there waiting.
Or spark.
Right. The moment an operator walks down the stairs and flips on a standard, non-explosion-proof light switch, the resulting detonation would literally blow the foundation apart.
That is terrifying.
Because the risk of this invisible pooling is so high, the standard simply outlaws basements entirely. The primary floor must be at grade to allow heavy vapors to diffuse outward and to allow gravity drainage of spills.
That makes the stakes incredibly clear. Now let's talk about holding the heavy equipment up.
Structural supports.
Yeah, if you have a 5,000-gallon mix tank on the second floor, it is being supported by heavy structural steel columns. The code demands that load-bearing supports for vessels be protected. But if a fire breaks out, I mean, steel seems tough, but it really isn't, is it?
Not under thermal stress, no. Structural steel is incredibly strong at room temperature, but it is highly susceptible to heat.
How susceptible?
At roughly 1,000 degrees Fahrenheit. Which, by the way, is a temperature easily reached within minutes during a solvent pool. Fire steel loses about 50% of its load-carrying capacity.
50%? In minutes?
Yes. It begins to plasticize and buckle. And if those steel legs buckle, that 5,000-gallon tank collapses, instantly rupturing and dumping its entire massive payload of fuel directly onto the fire.
Which just multiplies the disaster exponentially.
Exactly.
So how do the layout engineers and the contractors actually protect that steel?
The standard offers a few paths. First, proper drainage, to ensure a burning spill flows away from the columns before it can even pool and heat them up.
Simple enough.
Second, you can use specialized fire-resistive construction around the steel, like encasing the columns in concrete, or applying what we call intumescent fire-resistant coatings.
Intumescent coatings, those are fascinating. I've read a bit about them, but how do they actually work in practice?
Well, they look like thick industrial paint when applied, just normal paint. But when they are exposed to extreme heat, a chemical reaction occurs. The coating rapidly expands and swells up to maybe 50 times its original thickness.
50 times?
Yeah, it transforms into this dense carbon-based char foam. And this foam acts as a highly effective thermal insulator, keeping the steel underneath cool enough to maintain its structural integrity for 1 to 2 hours, depending on the rating.
That is basically magic paint.
It really is. Alternatively, you can install a dedicated NFPA 15 water spray system designed explicitly to drench those specific columns.
Just to keep them wet.
Right. It uses the latent heat of vaporization of the water to actively pull heat out of the steel during a fire.
Okay, so we have an above-ground, fire-protected, non-combustible box. Now we have to deal with the air inside it, because the ventilation requirements are incredibly stringent. And I know this is where HVAC engineers face their biggest battles.
Oh, absolutely.
If you have an enclosed process area handling Class I liquids, it must be continuously ventilated. The baseline standard is a mechanical exhaust rate of not less than 1 cubic foot per minute per square foot of solid floor area.
Correct.
But crucially, the standard explicitly mandates where that suction must happen.
Yes, it demands that the suction take place at floor level.
Not the ceiling.
Exactly. Again, we refer back to the physics of vapor density. The hazardous, ignitable vapors are pooling around the ankles of the operators.
Right.
If an HVAC engineer designs a beautiful system with exhaust registers way up on the 20-foot ceiling, they are just exchanging clean air while leaving the explosive hazard completely untouched down on the floor. You have to physically sweep the floor with the ventilation system.
And obviously you have to pull fresh air in to replace what you're exhausting.
Correct. And the placement of that makeup air is just as vital as the exhaust. If the fresh air supply vent is located too close to the floor exhaust vent, the air will short circuit.
What does that mean, short circuit?
The fresh air comes in and gets instantly sucked right back out, leaving the rest of the vast factory floor completely stagnant. The design must ensure the air movement physically sweeps across all portions of the floor to prevent localized pockets of vapor accumulation.
But I have to push back on this from an owner's perspective. Think about the pure economics of this rule.
The energy penalty.
Yes, if I have a massive 50,000 square foot facility in Chicago in the dead of winter, I am mandated to pull 50,000 cubic feet of air per minute every single minute and blast it completely out of the building into the atmosphere.
That's the rule.
That air is heated. I paid to heat it. And to replace it, I'm sucking in 50,000 cubic feet of freezing, 0-degree outside air that I instantly have to spend massive amounts of natural gas to heat. The energy penalty is astronomical. Can't we just filter and recirculate the air?
The energy cost is undeniably one of the most painful operational expenses for these facilities. Owners constantly want to recirculate to save on heating and cooling.
Naturally.
But standard recirculation is a death sentence in this environment because you are just taking explosive vapors and pumping them back into the room.
Oh, right.
However, the standard does offer a highly engineered compromise. Recirculation of exhaust air is permitted, but only if you install a continuous, fail-safe vapor monitoring system.
Okay, how does that system work in practice?
The facility must be equipped with optical or catalytic sensors that constantly sample the chemical composition of the air right in the exhaust ducts. As long as the concentration of flammable vapors remains below 25% of the lower flammable limit, the LFL, the system can safely recirculate.
So that 25% threshold gives you a massive 75% safety margin before the air actually becomes explosive.
Exactly. But if a spill occurs and the vapor concentration spikes above that 25% limit, the system must trigger an automatic, immediate physical response.
Like what?
It sounds an alarm. Motorized dampers instantly slam shut to block the recirculation path, and the system diverts to 100% full exhaust directly to the outside atmosphere.
That is a phenomenal piece of engineering.
It's a brilliant way to save energy, but those electronic safety interlocks must be absolutely bulletproof.
Yeah, they have to be. And speaking of explosions, we have to talk about deflagration venting. If a building handles Class IA liquids or processes materials above their boiling points or has combustible dusts, the standard says a deflagration hazard exists. Now, deflagration is a specific scientific term.
It is.
It means an explosive combustion wave that travels rapidly, but at subsonic speeds, slower than the speed of sound. If that pressure builds up inside a heavily reinforced, rigid concrete box,
The concrete box will eventually fail catastrophically. It will shatter, sending massive lethal slabs of concrete and steel shrapnel flying in every direction.
just a giant bomb.
Right. To prevent this, the building must be designed to intentionally fail in a controlled manner. This is deflagration venting.
So you are literally building weak spots into the fortress.
Precisely. You design specific sections of the walls or roof using lightweight panels, or panels held in place by specialized low-pressure relieving fasteners.
Okay.
When the internal pressure from an explosion begins to spike, these specific panels blow outward almost instantly, creating a path of least resistance.
Safely directing the blast.
Exactly. This safely directs the immense blast wave and the fireball outside into a designated safe area, rather than allowing the pressure to build to the point where it destroys the primary structural integrity of the entire building.
It's like engineering a massive pressure relief valve for a skyscraper.
That's a great way to picture it.
Now, with all these vapors present, the electrical systems become a massive ignition risk. NFPA 35 points heavily to NFPA 70, the National Electrical Code, to dictate hazardous area classifications.
And those classifications map perfectly to the physical behavior of the chemicals.
How so?
Well, where Class I liquids are processed in open equipment, the area immediately surrounding that equipment is classified as Class 1, Division 1.
Okay, Div 1.
That means ignitable concentrations of vapors are expected to exist under normal, everyday operating conditions.
Just as a matter of routine.
Right. So everything within that zone, typically a 5-foot bubble around the equipment, must be heavily armored, explosion-proof electrical gear. Switches must be sealed so any internal electrical arc is contained and cannot ignite the outside air.
But the code also extends a Class 1 Division 2 classification further out.
Oh, it does.
It generally extends from 5 feet out to 8 feet horizontally. And crucially, it covers the entire space up to 3 feet above the floor, extending out 25 feet horizontally. Because, as we established, the vapors sink.
Exactly. The code anticipates that heavy vapor creeping across the floor. In a Division 2 area, explosive vapors aren't normally present, but they could be under abnormal conditions, like a leak.
Right.
But here is the real challenge for the contractors. Buying explosion-proof computers, switchgear, and control panels for an entire vast factory floor is astronomically expensive.
Oh, I bet.
So engineering provides a workaround via NFPA 496.
Positive pressure rooms. I love this concept.
It is brilliant in its simplicity. If you need to place standard, non-rated electrical equipment, like a standard PC or a master control board, into a hazardous classified area, you build a sealed room for it.
Okay.
You then pump clean, uncontaminated outside air into that room so that the atmospheric pressure inside the room is physically higher than the pressure out on the factory floor.
Because the pressure inside is pushing outward.
Exactly. The heavy explosive vapors on the floor simply cannot penetrate the room against that pressure gradient. Every time a worker opens the door, the clean air forcefully rushes out, physically pushing the hazard away.
That's just so elegant. Okay, so we have constructed the ultimate building. The foundation is mapped. The structural steel is insulated. The ventilation is sweeping the floor, and the electrical is pressurized.
We have the box.
We have the box. But an empty building doesn't manufacture organic coatings. We need to move thousands upon thousands of gallons of volatile liquids through this space. That brings us to the mechanical heart of the facility: process equipment, piping, and operations.
Yes. And this is where mechanical contractors must be absolutely meticulous.
Let's get into it.
Transferring class 1, 2, and 3, liquids from the bulk storage tanks to the process areas, must be accomplished through closed piping systems. You can use gravity flow, or you can use mechanical pumps. But both introduce massive risks if a pipe bursts.
Let's start with gravity flow. If you have a massive storage tank on the second floor feeding solvent down to a mixed tank on the first floor, gravity is providing the motive force.
Right.
But gravity doesn't have an off switch. If a pipe breaks on the first floor, that second floor tank is just going to keep violently emptying its contents until it is completely dry.
Which is exactly why the standard mandates that gravity flow systems must be equipped with fail-closed, remotely actuated valves.
Fail-closed.
Yes, this is a critical engineering concept. A fail-closed valve requires constant active energy, usually compressed air or an electrical current, just to hold it open.
Okay, so it wants to close.
Exactly.
Yeah.
If an emergency occurs, or if the facility loses a compressor, or if a fire melts the pneumatic line,
the energy holding the valve open vanishes.
right, and a massive mechanical spring inside the valve immediately takes over and physically slams the valve shut. It inherently defaults to a safe, closed state without requiring any human intervention or power source.
That's incredibly smart. You also need manual emergency shutoffs near the point of use and at the storage tanks, right?
Yes, redundancy is key.
And what if you were using pumps instead of gravity?
You need a similar rapid shutdown philosophy. You must install emergency switches to immediately kill power to all pumps and stop the flow of fuel. These switches have to be strategically located at the exits from the process areas, at other safe locations, and right at the pumps themselves.
Now, what about moving liquids by pressurizing a tank and pushing the liquid through the pipe with gas? Pressurized transfer.
That is permitted, but the code introduces a severe restriction based on the fire triangle.
The fire triangle: fuel, heat, oxygen.
Right. If you are using pressurized gas to push a highly flammable Class I liquid through a pipe, you absolutely cannot use compressed air.
Because air is 21% oxygen.
Exactly. If you use compressed air to push a volatile solvent, you are actively mixing the fuel with pressurized oxygen inside a steel pipe.
Oh, wow.
If a single spark is generated by static electricity, or if there is mechanical friction in a valve, the entire piping system instantaneously becomes a pipe bomb.
Literally a pipe bomb.
Yes. The standard mandates that you must use inert gas systems, like nitrogen or argon, for these transfers.
Because it displaces the oxygen.
Right. The inert gas pushes the liquid just as effectively, but it chemically displaces all the oxygen, rendering the environment completely non-ignitable, regardless of sparks.
That is a crucial distinction for process engineers. Specify nitrogen, never air.
Never air.
Now let's talk about the physical pipes themselves. The standard dictates they must be made of steel or other approved ductile materials, but here is the massive red flag, the absolute prohibition. Cast iron valves, fittings, and pipes are strictly prohibited.
Banned entirely.
I really want to dig into the why here, because cast iron has been the backbone of global plumbing for over a century. Why ban it here?
It comes down to the metallurgy and the carbon content of the metal.
Okay.
Standard cast iron has a high carbon content, which makes it incredibly rigid and strong under compression, but it also makes it exceptionally brittle. It has almost no ductility.
Ductility meaning?
A metal's ability to bend, stretch, and deform under physical stress without breaking. Steel is highly ductile.
So if a forklift accidentally bumps a steel pipe, the pipe might dent or bend, but it will hold the liquid.
Right. But if that same forklift bumps a cast iron valve, or if there is a sudden sharp pressure hammer inside the fluid line, the cast iron doesn't dent.
It snaps.
It catastrophically fractures. It shatters like glass, instantly dumping hundreds of gallons of explosive fuel directly into the workspace.
That is terrifying.
Furthermore, consider the thermal shock during a fire. If a fire breaks out, the piping gets extremely hot. Then, the fire department arrives and hits that red-hot cast iron valve with a high-pressure stream of incredibly cold water.
Oh, the rapid temperature change causes the metal to contract violently.
And because cast iron is brittle, that rapid thermal contraction causes it to crack and fail instantly.
Which suddenly feeds an existing fire with a massive influx of fresh fuel.
Exactly. Steel, being ductile, can absorb that thermal shock and maintain its structural integrity much longer. This is why the standard draws a hard, unforgiving line. No cast iron in flammable liquid service.
It perfectly illustrates the gap between commercial plumbing and hazardous material engineering.
It really does.
And to prove that the piping is flawless before a single drop of chemical is introduced, the contractors must perform hydrostatic testing. The standard requires all piping to be hydrostatically tested to not less than 1.5 times the expected working pressure.
And it has to hold that massive overpressure for a minimum of 30 minutes without a single drop leaking.
And the key word there is hydrostatic, meaning using water to test the pipes, not pressurized air.
Right. The physics of the testing medium is literally life or death here. Water is an incompressible fluid. If you pump a pipe full of water to 1.5 times its rating and the pipe fails or a weld cracks, the water just squirts out. The pressure drops instantly to zero. It's wet, but it's safe.
But air.
Air is compressible. If you pneumatically test a pipe with air to 150 psi, you've packed a massive amount of potential energy into that space. If the pipe fails during an air test, that compressed gas expands violently and instantly.
Like an explosion.
It creates a lethal shock wave and turns metal fragments into deadly shrapnel. Contractors must strictly adhere to hydrostatic testing to protect their workers during commissioning.
Phenomenal breakdown. So the pipes are proven safe. Now let's look at the vessels where the actual chemistry happens. The reactors, the kettles, and the thin-down tanks.
Cookie pots.
Yeah, exactly. Manufacturing complex resins often requires adding significant heat to drive chemical reactions. If a facility is using direct-fired heaters, meaning there is literally a furnace burning natural gas directly under the kettle, the standard demands serious safeguards.
The most critical safeguard is a flame-out sensor on the firebox.
What happens during a flame-out?
It's a terrifying scenario. Imagine the burner under a massive kettle is firing normally, but a draft, or a fuel hiccup, extinguishes the actual flame, yet the gas valve remains open.
Oh no!
You're now pumping massive volumes of unburned natural gas into an incredibly hot, enclosed firebox. The moment that gas cloud finds a hot enough surface or an ignition source, the resulting explosion will destroy the furnace and potentially rupture the entire kettle above it.
So how do the sensors work?
Modern sensors detect the loss of the ultraviolet or infrared signature of the flame and instantaneously shut off the main fuel supply.
That's a lifesaver. And the physical area under the kettle where the furnace sits has to be completely curbed and sealed off from the main operating flow, right?
Yes.
Because they don't want a solvent spill from a totally different process running across the floor and pouring down into the open flame of the furnace.
Exactly. Keep the fuel away from the fire.
But here is the process hazard that I find absolutely terrifying. The standard explicitly dictates that reactors and thin-down tanks must be designed and operational procedures established to prevent violent foaming when materials are added to hot reactor contents.
Violent foaming.
I mean, violent foaming sounds like a benign science fair volcano, but in an industrial setting, it's lethal, isn't it?
It is one of the most unpredictable, sudden, and dangerous events that can happen in a batch chemical process. Violent foaming is not just bubbles. It is a rapid, forceful expansion of gas and boiling liquid caused by a runaway thermodynamic reaction.
When does that usually happen?
It typically occurs when an operator adds relatively cold, liquid, or solid ingredients into a reactor that already contains extremely hot fluids.
Okay, wait. It is the exact same physics as dropping a frozen turkey into a deep fryer on Thanksgiving.
That is the perfect analogy.
Right.
The intense heat of the reactor instantly vaporizes the cold material or the moisture within it. As liquid turns to gas, it expands hundreds of times in volume in a fraction of a second. This massive volume of gas forcefully ejects the boiling, flammable liquid contents right up and out of the top of the vessel.
And traditionally, an operator would be standing right there on a catwalk, manually dumping bags of ingredients through an open hatch.
Exactly. If violent foaming occurs, that operator is hit with a geyser of boiling solvent.
That's horrific.
It causes catastrophic thermal and chemical burns and simultaneously generates a massive explosive vapor cloud in the immediate vicinity.
So how does the standard prevent that?
To prevent this, the standard pushes for engineered closed-addition devices. Instead of an open hatch, you use a mechanical screw feeder or a rotary airlock valve to add solids slowly, allowing the operator to stand behind a protective shield or in a control room entirely.
That makes so much sense. Furthermore, mixing tanks that utilize heating systems must have safe operating temperature limit controls, right?
Redundant sensors.
Right. Redundant sensors that automatically kill the heat supply if the temperature exceeds a safe limit. And there is a tragic history behind this specific rule. This is where we see the direct influence of the U.S. Chemical Safety Board, the CSD.
The Danvers incident.
Yes, in 2006 in Danvers, Massachusetts. An ink and paint facility was heating a mixing tank overnight. The primary temperature control failed, the heat stayed on, and the tank boiled uncontrolled for hours, completely filling the building with vapor.
And then?
A spark eventually ignited it, and the explosion leveled the facility and damaged dozens of homes nearby. Following the forensic analysis, the NFPA updated these codes to mandate these automatic, redundant, high-temperature shutoffs.
It is the grim reality of industrial safety codes. They are often written in the ashes of past disasters.
That's so true.
The Danvers explosion proved that you cannot rely solely on an operator noticing a rising gauge, especially on night shifts. The automatic high-temperature shutoff is a direct, engineered countermeasure to mechanical failure and human operational drift.
Okay, so we have built the plumbing, the reactors, and the fail-safes for standard solvents. But the organic coatings industry relies on some incredibly volatile, highly specialized chemical formulations that completely refuse to play by the normal rules.
The wild cards.
The wild cards. Section 8 of the standard deals with special hazards, nitrocellulose, monomers, and organic peroxides. Let's start with nitrocellulose.
Okay.
What makes this stuff so uniquely terrifying that it gets its own dedicated handling protocol?
Well, nitrocellulose is fundamentally a nitrated cellulose. It is typically manufactured by treating cellulose like cotton linters or wood pulp with nitric and sulfuric acids.
Okay, so it's modified wood or cotton.
Right. The resulting compound has a nitrogen content ranging from roughly 10.5 to 12.6% by weight. It is an incredibly valuable, fast-drying, film-forming binder resin used in specialized lacquers and coatings.
What?
But its hazard profile is completely alien compared to a standard liquid solvent. Standard solvents require an external spark to ignite. Nitrocellulose is fiercely sensitive to something much simpler: frictional heat.
Frictional heat. Wait, so we aren't just worried about an electrical arc or an open flame. We are worried about the physical act of rubbing two things together.
Precisely. And this dictates exactly how operators must handle the material. The standard is incredibly blunt. You absolutely cannot drag, push, or slide a metal drum of nitrocellulose across a hard concrete floor.
Because the simple metal-on-concrete friction of a sliding barrel generates localized heat at the bottom of the drum.
And that localized heat transfers through the thin seal wall and can instantly ignite the highly sensitive nitrocellulose inside.
Just from sliding it.
Yes. The standard dictates that drums can only be moved by rolling them on their lower chime, the reinforced elevated rim at the base of the drum, which minimizes contact area.
The rules for equipment are just as strict, aren't they?
Very much so.
Like, if a worker uses a wheeled hand truck, it must be explicitly fitted with a grab mechanism to securely hold the top of the container. If a forklift is used, it must have a properly designed drum-holding device. You cannot risk a drum slipping and hitting the ground.
Because the physical shock and friction of a drop are enough to initiate combustion.
And if it does ignite, the resulting fire is fundamentally different from a solvent fire. Right.
Completely different.
Such requirements demand that inside storage rooms for nitrocellulose be physically separated from production areas by 2-hour fire-rated walls. But the most critical element is the fire suppression system.
That deluge.
Yeah. The room must be protected by an automatic sprinkler system, preferably a high-speed deluge system, capable of delivering an incredibly dense water application rate, 0.35 gallons per minute per square foot over the entire storage area.
That is a lot of water.
To put that math in perspective, 0.35 gallons per minute per square foot is a torrential, hurricane-level downpour.
It is.
Why does nitrocellulose require such an overwhelming volume of water compared to other chemicals?
Because of its molecular structure. When nitrocellulose burns, the molecule actually decomposes and releases its own oxygen.
Oh, wow. So the fire is feeding itself from the inside out.
Exactly. The traditional fire triangle requires external oxygen. If a normal solvent catches fire, you can spray an AFFF foam blanket over it to cut off the ambient air, and the fire smothers and dies.
But not this stuff.
If you spray foam over burning nitrocellulose, it just keeps burning fiercely right through the foam because it doesn't need the outside air. Smothering is completely ineffective.
So what do you do?
The only way to stop a nitrocellulose fire is through massive, overwhelming thermal extraction. You have to use an immense volume of water to forcefully pull the heat out of the reaction, dropping the temperature below the ignition point faster than the chemical decomposition can generate new heat.
That requires a literal deluge.
Yes.
That makes the stakes so high. But if dry nitrocellulose is basically a low-grade explosive, why does the standard allow solvent-wet or water-wet versions in the factory? I noticed the definitions make a sharp distinction between dry nitrocellulose and wet nitrocellulose.
Well, dry nitrocellulose is practically an explosive and is generally avoided in all coating operations. To make it viable for industrial transport and use, the industry utilizes wet nitrocellulose.
Okay.
The raw material is wetted with at least 25% by weight of either water or, more commonly, a flammable liquid like alcohol, isopropyl, or toluene.
Wait. You intentionally wet an explosive solid with a highly flammable liquid solvent to make it safer? That sounds completely counterintuitive.
It sounds absurd, I know, but it is deeply rooted in thermodynamics. The wetting agent, even if it is a flammable solvent like alcohol, acts as a critical thermal buffer.
A buffer against the heat.
Exactly. If the drum is exposed to friction, radiant heat, or ambient temperature spikes, that heat energy cannot immediately attack the solid nitrocellulose. First, the heat must vaporize the liquid wetting agent.
Oh, I see.
This phase, change from liquid to gas, absorbs a massive amount of thermal energy. The liquid acts like a thermal sponge, buying the operator's crucial time before the solid material reaches its ignition temperature.
However, that buffering action introduces a brand new mechanical hazard, doesn't it?
It does.
If the drum gets hot, that wetting agent vaporizes and turns into a gas inside the sealed drum. As the gas expands, the internal pressure skyrockets, which can violently pop the lid off the drum, exposing the material.
Which leads directly to the standard's strict rules on inventory management. Nitrocellulose must be stored in such a manner that the stock is constantly rotated. First in, first out.
Keep it moving.
The oldest material must be used first, and the standard strongly implies it should not be stored for extended periods, generally not more than 2 years. Because over time, even in a sealed drum, that liquid wetting agent can slowly evaporate or leak out.
And if a drum sits forgotten in the back corner of a hot warehouse for 3 years, it dries out. And dry nitrocellulose is a disaster waiting to happen.
It's a bomb. The standard even dictates the exact protocol for sweeping the floor.
Really? Sweeping?
Yes, you cannot just take a broom, sweep up spilled nitrocellulose dust, and throw it in a standard plastic trash can. The friction of the broom itself is a hazard.
Oh my goodness.
Sweepings must be immediately wetted down with water or solvent and placed in a specialized covered metal container. Allowing distillation solids or minor spills to simply dry out on the factory floor is a recipe for a horrific flash fire.
And for the mechanical engineers designing the process equipment, if the plant uses high-energy dispersion equipment, like 2 roll mills, to physically crush and process nitrocellulose into a paste, the code is unforgiving.
Very.
Those mills must be located in a detached building or a heavily separated non-combustible structure. And you must design a remote, manually operated deluge water spray system aimed explicitly at that mill.
Right.
If the friction of the rollers ignites the batch, the operator pulls a lever from a safe distance to instantly flood the machine.
Nitrocellulose requires total operational respect, but it's only the first wildcard. Section 8.2 covers monomers.
Monomers.
Monomers are a different breed of chemical beast. These are highly reactive molecules like styrene, acrylates, or vinyl chloride, whose fundamental chemical nature is a desire to link together to form long, complex chains called polymers.
And linking molecules together is an exothermic reaction. It releases heat.
A tremendous amount of heat. Under controlled conditions inside a reactor, you manage that heat. But if that polymerization process accidentally triggers inside a bulk storage tank, it creates a deadly positive feedback loop.
A runaway reaction.
Exactly. The initial linking generates heat. That heat speeds up the reaction of the remaining molecules. The faster reaction generates even more heat. This leads to a violent, runaway self-polymerization.
And if this happens inside a closed storage tank?
The liquid rapidly boils, the pressure builds at an uncontrollable rate, and the tank undergoes a catastrophic violent rupture.
So how do you stop these molecules from linking up while they are just sitting in storage waiting to be used?
The chemical manufacturers add specific compounds called inhibitors. You can think of inhibitors as molecular bouncers.
Bouncers, nice.
They actively intervene and stop the monomer molecules from reacting with each other. But there is a massive catch that owners must monitor. These inhibitors naturally degrade and lose their effectiveness when exposed to heat or over long periods of time.
So if a bulk tank of monomer is sitting outside in the brutal Texas summer sun, the heat degrades the inhibitor.
Yes.
Once the inhibitor is depleted, the bouncers are gone, and the runaway polymerization begins spontaneously.
Exactly. This is why the standard mandates that tanks storing liquid monomers must be designed with specialized emergency relief vents.
To handle the pressure.
Right. These vents must be mathematically sized to relieve not just normal vapor pressure, but the massive explosive evolution of gas, boiling liquid, and vapor that results from a full runaway polymerization. Additionally, engineers might need to design active cooling systems, like chilled water jackets or reflective insulation, simply to keep the liquid cool enough so the inhibitors don't break down in the first place.
And our final wild card in Section 8 is organic peroxide formulations. These are incredibly unstable, reactive organic compounds used as catalysts.
They're essentially chemical initiators. They're designed to be highly reactive.
Right.
Some are so profoundly sensitive that they will begin to decompose violently just from exposure to ambient room temperatures or minor mechanical shock.
Just room temperature.
Yeah. They're also powerful oxidizing agents, meaning they supply their own oxygen to a fire, and they can react explosively if they accidentally come into contact with reducing agents or heavy metals.
So what's the defense?
The standard acknowledges their extreme danger and refers engineers directly to NFPA 400, the Hazardous Materials Code, for their specific storage requirements. But the core lesson is absolute isolation, relentless temperature control, and a microscopic attention to preventing cross-contamination.
Okay, so we have engineered countermeasures for every physical threat. We've mandated floor-sweeping ventilation to handle heavy vapors. We've banned brittle cast iron to prevent shattering. We've built deluge systems to drown nitrocellulose, and we've chilled our monomers.
We've built a fortress.
We have built the ultimate impenetrable chemical cage, but there is an invisible enemy that can effortlessly bypass all of our physical walls, all of our steel pipes, and all of our sensors. We touched on it briefly at the start, but we need to dedicate serious time to it now because it is the most insidious hazard in the entire code.
Chapter 9.
Section 5, the spark. Control of ignition sources. This is Chapter 9 of the standard, and we are talking about this terrifying reality of static electricity.
Static electricity is a uniquely terrifying hazard in organic coatings manufacturing because it isn't an external threat. It is generated by the very act of operating the facility.
By doing the work.
Right. The physical phenomenon is called triboelectric charging. When you pump a liquid solvent through a steel pipe, the friction of the fluid molecules rubbing against the interior wall of the pipe actively strips electrons away.
From the liquid.
Yes. The liquid literally generates and accumulates a massive electrostatic charge simply by flowing. Pouring a solvent into a tank, mixing it with a high-speed agitator, filtering it, all of these normal actions build up static charge.
And if that high-voltage static charge accumulates on a metal tank or a pipe, it desperately wants to find a path to the earth.
It wants to ground itself.
If there is a tiny physical gap between the charged pipe and the ground, the electricity will arc across that gap in the form of a spark. And if that microscopic spark occurs in a Division 1 area filled with explosive vapors,
you have an instantaneous detonation. The entire engineering goal of Chapter 9 is to build a safe, invisible, highly conductive highway into the earth so that the static electricity never has a reason to jump across a gap and create a spark.
Bonding and grounding.
This is the science of bonding and grounding. Section 9.5.1 states unequivocally that all equipment, tanks, machinery, and piping where an ignitable mixture might be present must be bonded together and connected to a ground.
And the standard doesn't just suggest it, it provides exact engineering resistance metrics that must be tested and verified.
Yes, the numbers here are critical for the electrical contractors. For a metallic grounding path, like a copper wire connecting a steel tank to a grounding rod, the electrical resistance to ground cannot exceed 25 ohms.
25 ohms.
For a non-conductive or semiconductive grounding path, It cannot exceed 1 million ohms, or 1 megohm. The physical connection has to be utterly flawless. You can't just wrap a wire loosely around a pipe and call it grounded.
Right.
The standard specifies that permanent grounding connections must be made with heavy-duty electrical cable lugs, bolted clamps, brazing, or welding. It must be mechanically robust so it cannot be accidentally knocked loose.
But where it gets really tricky is with portable equipment like grounding a 55-gallon drum before you pour from it.
Oh, definitely.
The standard dictates that temporary bonding clamps must be the opposed point type. This is a tiny detail that layout engineers and safety managers must mandate on the procurement sheets.
It is a massive detail, actually.
Why is an opposed point clamp so functionally different from, say, a standard alligator clip you'd use on a car battery?
Think about the surface of that 55-gallon drum. It is made of steel, but it is covered in a thick layer of industrial non-conductive paint.
Okay.
If an operator clips a standard flat-toothed alligator clip to the rim of the drum, the teeth clamp down on the paint. You have a solid physical connection, but because paint is an insulator, you do not have an electrical connection.
Oh, so the drum is completely electrical isolated.
Exactly. It's acting as a massive capacitor building up charge. An opposed point clamp is designed with hardened, needle-like steel points. When the operator tightens the clamp, those sharp points physically bite through the layers of non-conductive paint and dig deeply into the bare steel beneath.
That makes perfect sense.
This guarantees true metal-to-metal contact, ensuring the static charge can flow safely to ground. It is a tiny mechanical detail that separates a safe liquid transfer from a catastrophic spark.
And it isn't just the liquids that generate static. The code highlights that powders are a massive threat.
Powders, yes.
Think about the manufacturing process. You have a vat of liquid solvent, and you need to add bags of dry pigment or thickening powder to create the paint. The simple friction of the dry powder sliding out of the paper or plastic bag generates a massive electrostatic charge on the powder particles themselves.
This specific scenario is a notorious cause of devastating industrial fires. The standard explicitly warns against the manual dumping of powders directly into a vessel containing a class of flammable liquid.
Why is this so bad?
As the highly charged powder hits the surface of the flammable liquid, it can discharge a spark right at the liquid vapor interface, the absolute most dangerous place for a spark to occur.
Because that's where the vapor is richest.
Exactly.
To perform this action safely, the code demands strict chemical or atmospheric engineering. The standard uses a unit of measurement called the picosiemen. It says the liquid must have a conductivity greater than 1,000 picosiemens per meter.
Let's translate that.
Please do.
A picosiemen is a measurement of electrical conductivity. If the liquid has high conductivity over 1,000 psm, it means the liquid itself acts like a wire.
Oh, I see.
As the charged powder hits the liquid, the static charge instantly dissipates through the liquid to the grounded tank walls and safely into the earth.
But many highly refined solvents like toluene or xylene are excellent insulators. They have virtually zero conductivity.
Right. And if you dump charged powder into an insulating liquid, the static charge just sits on the surface of the liquid, accumulating until it arcs to the metal wall.
So what's the solution?
If you are using a low conductivity liquid, the standard mandates you must engineer an alternative solution. You either have to completely inert the internal vapor space of the tank with nitrogen gas, so even if a spark arcs, there is no oxygen to burn, or you must use specialized anti-static additives to artificially boost the liquid's conductivity above 50 picosiemens per meter, assuming there's no second phase like water present.
It illustrates how deeply the chemical engineers must collaborate with the safety engineers just to dump a bag of pigment.
And they have to be in constant communication.
And what about the physical mechanics of liquids falling through the air? The standard has a specific section on fill pipes.
Yes, Section 9.5.3 addresses a phenomenon known as splash filling. If an operator is transferring more than 60 gallons of a non-conductive class liquid into a large tank, they cannot just open a hatch at the top and let the liquid free fall through the air.
Because as the liquid falls, gravity breaks the solid stream apart into thousands of individual droplets.
Exactly. And as those thousands of droplets fall rapidly through the air, the friction generates and rapidly accumulates a massive static charge. It is essentially a high-voltage static electric waterfall inside the tank.
So how do you physically prevent that?
The standard mandates the use of engineered fuel pipes that extend all the way down to the bottom of the receiving tank. Instead of splashing from the top, you pipe the liquid down so it gently fills the tank from the bottom up.
Keeping it in a solid stream.
Right. This keeps the flowing liquid in a solid, continuous stream, eliminating the free-fall droplet separation and drastically reducing static generation. Furthermore, the bottom of that fill pipe is often designed with a 45-degree angle cut to ensure the liquid flows smoothly across the bottom of the tank rather than jetting forcefully against the floor.
It is such a beautifully simple mechanical pipe fix to neutralize a complex, invisible electrical hazard.
Engineering at its finest.
But we have to talk about the hook we opened the show with, because this next rule absolutely blew my mind when I realized the scale of the danger. Section 9.5.4. Applying or removing plastic stretch wrap is strictly prohibited in any hazardous classified location.
The stretch wrap rule.
We all know the static cling of plastic wrap, but does it really generate enough voltage to cause an industrial explosion?
It absolutely does, and it is one of the most frequently overlooked hazards by floor personnel. Think about the physics of a capacitor. You have two insulators rubbing against each other. When you peel a tiny piece of plastic wrap off a bowl at home, you hear the crackle. You are generating static electricity.
Right.
Now, scale that up to industrial proportions. Imagine an operator forcefully peeling a massive 6-foot-tall sheet of heavy-duty industrial stretch wrap off a pallet tightly packed with metal drums. The immense surface area of that plastic being violently peeled apart generates an enormous electrostatic charge.
It's like rubbing a giant balloon on your hair, but with enough accumulated voltage to act as a detonator.
Precisely. The operator's body might even act as the conductive path for that charge. If that operator unwraps that pallet in a Class 1 Division 1 area, where invisible, heavier-than-air explosive vapors are hovering around their ankles, that seemingly innocent, everyday act of tearing plastic wrap can effortlessly generate a spark capable of igniting the entire vapor cloud.
That's terrifying.
Therefore, the standard unequivocally forbids it. Pallets must be unwrapped in safe, unclassified receiving zones before the drums are moved onto the process floor.
That is just wild, but it makes perfect scientific sense. It really forces facility owners to audit everything that happens on the floor as a potential ignition source.
Everything.
The standard even notes in Annex A that operators themselves are massive static generators. The human body is essentially a walking capacitor. The friction of your shoes on the floor or the movement of your clothes generates a charge.
Yes, people are a hazard.
The standard recommends wearable grounding devices, like conductive footwear or ankle straps, to ensure an operator's personal skin-to-ground resistance doesn't exceed 10 to the 8th power ohms. You literally have to ground the humans.
And you absolutely have to ground the vehicles.
Mm-hmm.
Section 7.6 covers power-operated industrial trucks, what we casually call forklifts.
Forklifts.
You cannot just drive a standard, off-the-shelf propane or electric forklift into a classified area. A standard forklift is a rolling ignition machine. The internal combustion engine, the hot exhaust manifold, the arcing of electrical relays, the friction of the brakes, they're all massive ignition sources.
So owners have to purchase heavily modified machinery.
Yes, you must use specially designated trucks. Type DX diesel trucks or Type IX electric trucks are rigorously engineered and armored to prevent any internal arcs, sparks, or hot exhaust from escaping the chassis and igniting ambient vapors in the room.
That must be so expensive.
It is, and it requires relentless enforcement by facility management. If a busy warehouse worker decides to save 5 minutes by driving a standard, non-rated forklift into a Division 1 mixing area just to quickly drop off a pallet of additives, they have instantly compromised the entire multi-million-dollar safety architecture of the building.
Which perfectly brings us to our final overarching theme. We have engineered the ultimate building. The ventilation is meticulously sweeping the heavy vapors off the floor. The pipes are ductile steel, not brittle cast iron. The vessels are grounded to a strict 25-ohm resistance. The nitrocellulose is wetted down and protected by a hurricane of sprinkler water.
It's all there.
But all of this flawless engineering is completely, utterly useless if the humans running the plant make a procedural mistake. Welcome to the failsafe: management, fire protection, and maintenance. This is Chapter 10 of the Standard. And the absolute cornerstone of this chapter is a strict administrative protocol called Management of Change, or MOC.
Management of change is arguably the most critical administrative control in modern chemical manufacturing. The standard dictates that comprehensive hazard evaluations must be completely repeated whenever materials, equipment, controls, or operating procedures are changed significantly.
Now, to a frustrated maintenance manager, that sounds like a bureaucratic nightmare.
It always does.
If a transfer pump breaks at 2 a.m., why can't I just grab a new pump off the shelf, swap it out, and keep production running? Why do I have to stop and do a massive engineering review?
Because a chemical facility, is an incredibly delicate, interwoven ecosystem of precise engineering calculations. Let's play out your exact scenario. A transfer pump breaks. The maintenance team replaces it with a new pump they found in the warehouse. But this new pump has a slightly higher horsepower motor and moves the liquid solvent 20% faster.
Okay.
To the maintenance team and the plant manager, that seems like a massive win. Faster pump equals faster production.
Right, they think they just optimize the process.
But they haven't consulted the safety engineers. By physically increasing the flow rate, the velocity of the liquid through the steel pipe is now 20% higher. As we discussed, fluid friction generates static electricity.
Oh.
By increasing the velocity, you have exponentially increased the rate of static electricity generation. The 25-ohm grounding system that was perfectly mathematically designed to dissipate the static generated by the old flow rate might not possess the capacity to dissipate the massive influx of static generated by the new, faster flow rate.
Oh, wow. So the static charge starts to bottleneck and accumulate on the pipe.
Exactly. Furthermore, the faster pump might now exceed the volumetric capacity of the downstream pressure relief valves.
Yeah.
If a blockage occurs, the relief valve can't vent the liquid fast enough, and the pipe ruptures.
Just from a pump swap.
By making one simple, seemingly beneficial, well-intentioned mechanical change without a formal management of change review, the maintenance team has completely invalidated the entire safety design of the system.
That is the literal butterfly effect in action. One slightly bigger pump leads to an ungrounded static charge, which leads to a catastrophic explosion.
Exactly.
MOC is the administrative pause button. It forces the mechanical engineers, the electrical engineers, and the safety officers to sit down and ask, if we alter variable X, how does it physically impact the mathematics of Y and Z?
Precisely.
What about everyday maintenance operations? Section 9.3 details hot work.
Hot work, which includes welding, cutting, grinding, or using standard power tools, is the deliberate introduction of a massive, obvious ignition source into a hazardous area. It is historically the leading cause of industrial fires during maintenance turnarounds.
So what's the rule?
The standard absolutely forbids hot work unless a written permit is formally issued by a specific person in authority. But crucially, that permit is not just a piece of paper you sign in an office. It can only be issued after a rigorous physical inspection of the work area has been conducted.
The area has to be sterilized of risk. Processed materials must be physically removed, equipment must be drained and purged, and the atmosphere must be scientifically tested with gas monitors to prove it is below explosive limits.
Annex B of the standard actually provides a sample safety work permit and a confined space entry permit. Facility owners should absolutely adopt these exact checklists.
Speaking of confined space entry, Section 13.2 covers what is arguably the most claustrophobic nightmare scenario in manufacturing, sending a human being inside a dark, chemical-coated tank to clean it.
Confined space entry is incredibly dangerous. The standard differs heavily to OSHA regulations, specifically 29 CFR 1910.146. If a worker must enter a tank, that tank must be completely isolated from the piping system using physical metal blinds. You can't just trust a closed valve.
You have to physically block the pipe.
Right. The tank must be inerted with nitrogen, or completely vapor-freed, using massive mechanical air movers before a human head crosses the plane of the hatch. But the standard includes a very telling note. It explicitly recommends that facilities prioritize the use of high-pressure mechanical washers and automated cleaning systems over human entry whenever physically possible.
Keep the human out of the chemical cage entirely. It's the smartest engineering solution. And when we talk about the ultimate failsafe, we have to look at the fire protection systems. Section 11 mandates heavy sprinkler systems governed by NFPA 13 and highly specialized foam suppression systems dictated by NFPA 11 and 16.
But there is a vital, often overlooked layout consideration here for the civil and plumbing engineers.
Oh, the drainage.
Yes. If a fire breaks out and you have massive deluge sprinkler systems suddenly dumping thousands of gallons of water per minute, combined with a foam system pumping out thousands of gallons of thick foam, where does all that liquid physically go?
Right. This is a classic secondary disaster scenario. If the floor drainage system isn't mathematically sized to handle the sheer immense volumetric output of the fire suppression systems, the building rapidly floods.
And because many flammable organic solvents are physically lighter than water, they float.
So the burning fuel literally floats on top of the rising sprinkler water.
Precisely. The burning liquid rides the crest of the flood, flowing out the doors, down the hallways, and spreading the fire into areas of the plant that were completely unaffected.
Well, it's a nightmare.
The drainage facilities must be rigorously engineered to handle the massive volume of the fire protection system discharge, routing that contaminated burning water through interceptor trenches to a safe remote containment basin on the property.
The final code point I want to touch on is in section 10.6. It is a single incredibly blunt sentence. All fires shall be investigated. Now, I understand deploying a team to investigate a massive multi-million-dollar blaze. But let's say a worker drops a heavy steel wrench on the concrete. It creates a tiny mechanical spark. A small patch of spilled solvent flashes, and the worker immediately grabs a fire extinguisher and puts it out in 3 seconds. No one is hurt, no equipment is damaged. Why would management spend valuable operational resources investigating a tiny, harmless, extinguished flare-up?
Because in safety engineering, there is no such thing as a harmless flare-up. Safety professionals refer to Heinrich's triangle, which illustrates that for every major catastrophic disaster, there are hundreds of minor near misses that preceded it. That tiny 3-second fire didn't happen by accident. It is a glaring, flashing red light highlighting a critical failure in the engineered controls.
It's a symptom of a much larger disease.
Exactly. The investigation must ask the hard questions. Why was there a concentrated flammable vapor cloud lingering on the floor in the first place? Did the mechanical floor sweeping ventilation system fail? Why was the solvent spilled and why wasn't it cleaned up?
And why a steel wrench?
Right. Why was a spark-producing steel wrench being used in a Division I area instead of a non-sparking brass tool? If management simply high-fives the worker for putting the fire out and sweeps the incident under the rug, the underlying mechanical and procedural failures remain completely unresolved.
And the exact same failure chain will happen again.
But next time, that dropped wrench might ignite a 5,000-gallon vapor cloud instead of a puddle. Investigating every single fire, regardless of its size, is the only way you identify the microscopic cracks in your armor before the entire structure shatters.
It is about relentless vigilance. So what does this all mean for the professionals listening? Let's trace the incredible engineering journey we've just taken. We started by dissecting the fundamental chemistry of our enemy, understanding the critical difference between a flash point and a fire point, and realizing that the simple act of adding heat to a process fundamentally rewrites the physics of the hazard.
Yes, the chemistry dictates the real estate.
Exactly. We strategically sited the building on the property map, respecting the massive, mathematically driven setback distances required to shield our neighbors from blast waves, and ensuring topographical drainage protects the surrounding environment.
We then built the physical box, enforcing the absolute ban on subterranean basements to prevent heavy vapor pooling, fortifying load-bearing steel columns with expanding intumescent char coatings, and engineering a massive, energy-intensive mechanical ventilation system designed to meticulously sweep explosive vapors right off the factory floor.
We relieved the pressure of inevitable explosions with sheer blowout panels, and we held back the invisible vapor monsters using positive pressure clean rooms for our electrical gear.
We plumbed the mechanical heart of the facility, completely outlawing brittle, shatter-prone cast iron in favor of highly ductile steel. We enforced fail-closed pneumatic valves that default to safety when the power dies, and we eliminated the oxygen from pressurized pipe transfers using inert nitrogen gas blankets.
We neutralized the terrifying, wildcards-drenching, self-oxidizing, friction-sensitive nitrocellulose under hurricane-level sprinkler densities and aggressively cooling unstable monomers to prevent runaway exothermic chain reactions.
We waged an invisible war against static electricity, bonding and grounding every single piece of metal to a strict 25-ohm resistors metric. We redesigned the simple geometry of fill pipes to eliminate the static generation of falling liquids. We mandated opposed point clamps to bite through insulating paint, and we outlawed the seemingly innocent yet highly capacitive act of removing plastic stretch wrap in classified zones.
And finally, we wrapped the entire multi-million-dollar physical structure in an impenetrable layer of administrative armor-enforcing management of change protocols to stop the butterfly effect of unreviewed modifications, requiring atmospheric testing for hot work permits, and demanding a rigorous forensic investigation of every single near-miss fire.
It is a phenomenal, awe-inspiring synthesis of chemical thermodynamics, structural design, mechanical engineering, and human behavioral psychology.
It really is. Which leaves me with a final, somewhat provocative thought for you. The layout engineers, the mechanical contractors, and the facility owners listening today. Oh, yeah. As we continue to design these increasingly brilliant, highly automated, mathematically foolproof facilities, as we blanket our volatile tanks in flawless inert gas, as we perfect the floor-level ventilation sweeps, as we use advanced optical sensors to monitor the vapor concentrations down to the thousandth decimal point, do human operators eventually become blind to the incredible latent lethal energy of the chemicals constantly surrounding them?
Wow. Does achieving perfect engineering inadvertently breed a dangerous operational complacency?
Exactly.
It is the ultimate unsolved paradox of safety engineering. The safer and more controlled you make the physical environment, the less dangerous it actively feels to the humans working inside it. And the less dangerous it feels, the more likely human operators are to subtly bypass the administrative rules, simply because they haven't seen a negative consequence in years.
It is a stark, lasting reminder. As an engineer or a contractor, you can build the absolute perfect cage for the beast. But a facility is ultimately only as safe as the daily, unwavering, paranoid respect given to the materials within it. Thank you for joining us on this exhaustive deep dive into the engineering and physics of NFPA 35. We hope this has provided the critical shortcut you need to design, build, and operate safer, stronger, and smarter facilities. Keep questioning the code, keep learning the physics behind the rules, and never ever forget what is waiting inside the cage.